Right, well, let's finish out this week with another application section. And we're going to do a little bit more with computer graphics. We did some in 1.8 and 1.9. We're just going to expand our toolkit now that we have a few more tools in the box. And you might recall back from section 1.8 and 1.9 that they had these huge layers, huge tables of transformations. And in my videos, I kind of waved my hands at those and said you shouldn't need the tables because it's really all about what happens to the unit square. So if you look at the two basic unit vectors, if you look at 1, 0 and you look at 0, 1, and you imagine that those sort of determine a unit square here. Then you say, oh, let's see, if I want to maybe have that flip over the y-axis, or the x2 axis, whatever you want to call it, and have it end up over here, then the big question really just becomes what happens to 1, 0 and what happens to 0, 1. Whatever happens to those, that will tell us how to make it happen for every other point. So you say the transformation of 1, 0 now is over here, the transformed version at -1, 0. And the transformation of 0, 1 is still at 0, 1. So the transformation matrix that flips all points over the y-axis will be the image of 1, 0, which is -1, 0, and the image of 0, 1, which is still 0, 1. So there's the transformation that flips things over the y-axis or x2 axis, and you'll notice that happens to be one of the things that's in the table. But if you want to do something that's not in the table, right, you do it that same way. Just draw the unit square, draw the new unit square, the transformed unit square, and just write down the images of 1, 0 and 0, 1. Okay, so much for the table. And there's one or two, well, just one really, that they didn't put in the table that I think is important. So let's take a little bit of time with the one that they left out, which is rotation. Suppose you want to take your unit square and just rotate it, 30 degrees or 192.7 degrees or whatever it is around the origin. So there's your original unit square, and the transformation that you want is just a rotation. So let's see how well I can draw a rotation here. Let's see, this is going to rotate over about like that, and this one's going to rotate up, so maybe about like that. I'm just noticing my square is kind of more of a rectangle, but pretend it's still a square. Okay, so there's my rotation. And the big question is, what happened to 1, 0? Where did it go? And where did 0, 1 go? And despite what it looks like in my picture, the length of the red vector and this first yellow vector, those are the same length. All I did was rotate. So they're both actually pointing to the edge of a unit circle. They both have a length of 1. They're a radius of a unit circle. So let me try to... oh boy. Let me try to draw that unit circle in there. The red vector, the purple vector, and both yellow vectors should all have, they do all have a length of 1. So they should all be pointing to a unit circle. Which makes things easier when we remember our trig, because we say, hey, I know where this point is. If this is rotated by theta, instead of being at 1, 0, it is now at, what's the x-coordinate of a point on the unit circle? X-coordinate's cosine. What's the y-coordinate of a point on the unit circle? Y-coordinate is sine. So the red vector that used to be 1, 0 is now at cosine theta, sine theta. And likewise, the purple vector has rotated over some. And if this distance right here is cosine of theta and this distance is sine of theta, notice those same distances exist over here. If you want to talk about the x coordinate, right here is the same as the y coordinate of our first point. So the x coordinate of the purple vector transforms into, and notice it's negative, so it transforms into negative sine of theta. I guess we're going purple here. Sorry, that's the x-coordinate. X-coordinate is negative sine of theta. I'm so used to sine going with y, but in this instance, the theta is over here, so the x-coordinate of this second vector is determined by sine. And likewise, the y-coordinate of this second vector matches the x-coordinate of the first vector. So that's just cosine. So our transformation to rotate is, and you'll know how much you want to rotate by. So you'll have like a 30 or something filled in here, so you'll know the numbers. But in general, cosine theta, sine theta, negative sine theta, cosine theta. Those are thetas. So that's a good one to have, and I wish they would have put it on the table. There's certainly homework questions in 2.7 that ask you to do rotations. So that's your basic rotation form. They did mention it back in 1.9, just as an example in the text. It never made it to the table, but so it is there. So jot that down. This matrix A, this cosine theta, negative sine theta, cosine theta. Make sure you have that in your notes somewhere. Just because, like I said, it's still just figuring out what happens to the image of the unit square, but it's not the easiest one to just sit down and figure out every time. So that's one that I kind of keep basically memorized in my head for working with these. And the other thing I wanted to point out in this video is just combining transformations. So let's say that you want to do the reflection. Let's see, let's get on the right layer. I want to do the reflection that we talked about earlier, reflection around the y-axis. And let's suppose after that you also want to do, so you're doing that to your points, to your xy points. After that, you also want to do a shear, and if you don't remember shears, they'd put something like there, let's say. So that leaves the x vector the same, but for the y vector it adds on half of the x coordinate. So if you want both of those to happen, you certainly can do multiply by the first matrix and then multiply by the second matrix. But if you're doing that over and over and over again for millions of points, it's a little more efficient, a lot more efficient actually, to combine your matrices. So you can actually figure out one transformation, a second transformation, a third transformation, a fourth transformation, and then multiply all those together into a single combined transformation. So here we've got a reflection, and here we've got a shear, And if we do just multiply those together, and then multiply that by coordinates, we'll get a shear reflection matrix, one that does both, and in the proper order, right? Because the order might matter here. So let's go ahead and multiply these together. Let's see, -1, 1, 5, 0, so that would be a -1 in that spot. -1, 0, so 0 in that spot. 0.5 and 1. Okay, so that wasn't a very exciting multiplication, but there's the matrix that will do both of those things in one fell swoop. You might have noticed in all these transformations that we have not done one that's pretty obvious. So we'll look at how to do that one in the next video.